Now, Mr. Sachidanand Prasad, uh, research fellow in ISER Kolkata, will be shortly recapping what we have done in this session. Yeah, now Sachidanand Prasad, it's up to you.
Yeah, thanks, Alapan. Very happy New Year to all, and thanks to Parthasarathi sir for giving a wonderful lecture from yesterday. And starting from the history and from the Greek problems and heading towards the modern algebra. So he started from Gauss's, some of the Gauss's result, like how can n-gon can be constructed. So, for example, he gave he cited a theorem of Gauss, like a regular polygon of n side is constructible if and only if it is in the form of 2 to the k or 2 to the k times p1 into p2 and the products of formats distinct primes. And he also so mainly the today's main theme of the lecture was a construction of n-gons via different approaches and how the algebra comes into the picture. So he showed what are the constructible numbers, and for example, uh, by constructing, he showed this just the this Gauss's result just I told. From citing this, we can prove that n-gon is not constructible, and by just using this, we can prove that the trisection of this angle in general is not possible by means of straightedge and compass, which was told by the Greek geometers. And then he talked about a lot of results explicit construction. When how do I do the explicit construction, like that the Gauss only showed the existential proof, like the this n-gon can be proved, n-gon can be constructed. He didn't show any construction. So by means of algebra, although we don't need also this construction, but and in some of the mathematician like Richard Holmes, they showed some constructions. And later he showed means he talked about number fields, which are now modern algebra, which is in field theory. So he so for number fields, and then extraction of basically how do I show that some number is constructible, and how do I extend some how do I extend this number fields from rational to irrational to reals and all those things, like extraction of a square root, like a is if a is given, so can we construct a square root a by means of this straight edge and compass. And at the end, he also showed that decagon can be constructed by means of straightedge and compass by showing that some number is constructible, which was the golden ratio for the square root of 5 minus 1 by 2. So that, and why it can be constructed, because root 5 is constructed, that he showed earlier, and 1 and 2 are also constructed, that is because of the number field. And hence this is a beautiful relation between the modern algebra and the very old Greek geometry. So I'm like eager to listen more from him. So heading to Parthasarathi sir. Thanks.
So thank you very much. I take up from that. That was a good recap of what we did in the morning. So we have this in front of us, the slide where, as I have already pointed out, the blue, the green, and the yellow. These are the three categories, where the blues are the thing where you can manage by allowing new methods like neusis or angle trisection. But then, of course, the question comes that these are somehow these Gaussian numbers, these 1734, they are related to this theorem of Gauss, related to Fermat prime, and related the other green, the blue numbers, they are related to ability to trisect instead of trisection, if I go beyond trisection, further subdivision, like subdivision into 5 equal parts, it can be shown that the horizon of constructibility for polygons, it expands further. And there you have the final result till now. This is by Andrew Gleason, the professor of Harvard University. This is a paper of 1988. And there you have this theorem. Very much generalization, very much you can say the next step of Gaussian theorem there. A regular polygon of n side can be constructed by ruler, compass, and angle trisector. See, Gauss put a boundary with ruler and compass and got it connected with Fermat prime. This gentleman here is generalizing it to ruler, compass, and angle trisector. And then the theorem is very much similar in spirit. If and only if the prime factorization of n is this 2 to the power r into 3 to the power s, p1, p2, pk, where this p1, p2, pk now are distinct primes greater than 3, and each of this specific form. These are just like those who are Fermat primes, these are called Pierre-Pont primes. 2 to the power t into 3 to the power u plus 1. Those were, in case of Gauss theorem, only ruler and compass related to Fermat primes and their distinct factors, the product of them. Here it is 2 to the power r into 3 to the power s, p1, p2, pk, where p's are distinct Pierre-Pont primes, where the primes are of this form 2 to the power t into 3 to the power u plus 1. That is the latest result for angle trisectors. You include that in the set of your tools. This is the expansion of your horizon. Further is this, a real cubic equation can be solved geometrically using ruler, compass, and angle trisector, if and only if its roots are all real. There is another very important point related to duplication of cube problem. Because if you start with a unit cube, its volume twice is 2, and you want an x such that x cube equal to 2. That's translation of the geometric problem into algebraic language, x cube equal to 2. So now you look at the theorem, it tells what? A real cubic equation can be solved geometrically using ruler, compass, and angle trisector. That means you will be able to construct that length using ruler, compass, and angle trisector if and only if its roots are all real. So duplication of cube. You see here, the angle trisector will not help us because the roots are not all real here. It's a cubic equation, rational coefficient, but roots are all only one real root, cube root of 2. So that is still beyond angle trisector. And it follows easily that regular n gone, any it need not be prime anymore, positive integer n, this can be constructed if, in addition to ruler and compass, that's the final generalization. You have already seen the restriction of angle trisector that gives you certain specific form of n to be tackled. Now it comes more general. Ruler, compass, and equipment is available to p-sect an angle for every prime p that divides phi n. Phi is the Euler tangent. So n gone, you want to calculate phi n first. See the prime divisors of this number phi n. And if you have instrument which p-sect an angle, that means equally divide the angle in p equal parts, then it is constructible by the ruler, the compass, and that particular instrument that is theoretically being proposed, a p-secting instrument. Like it's a trisecting instrument, trisectors, it's a p-secting instrument. One particular example, a small one, you see this 11 gone. According to this theorem, 11 is the number of proposed sides. Phi 11, you know, is 10. Phi of p is p minus 1. So Euler tangent. So phi 11 is 10. So its prime factors are 2 and 5. So you need a machine to quintisect, to divide it an angle in 5 equal parts. Once that is made available, using that, you can manage a construction of 11 gone. And this can be generalized. Not just ends with 5. Theoretically, now whether such a machine can be constructed is a different, again, engineering challenge. Mathematically, it is settled. Right? One example I would like to show you is this tomahawk quintisector. Tomahawk, you have seen it, trisects an angle. 2 tomahawks adjusted in this specific manner, as you can see here, it quintisects the angle TVE. The 2 tomahawks in the picture, try to understand, they are balanced in a specific manner. The end point of one is merged with the first midpoint of the this semicircular center. It is merged with that and placed accordingly. Then it can be proved these triangles you can see over there, that the triangles, they have the same angle at their vertex, actually quintisecting the. This can be I think I'll be able to show you the dynamic animation as well in this Mathematica Wolfram. Can you see this? Just a moment.
No, sir, it's the
Just a moment.
the same.
As the Mathematica is opening, can you see any new slide here? The tomahawk quintisector. The animation here, the dynamic animation. Can you see it to the left of the screen?
No, sir, it seems the same.
This new thing is not being visible, right? So okay, let us leave it then. Let us leave it then. It is. Okay, fine. So, well, at least I can give you the idea of the basic structure. It's engineering thing to make such machines, whether beyond quintisecting, then you divide it in 7 equal parts and 11 equal parts and on, how to do that, what should be the machine. But that's completely beyond mathematics. Those are engineering aspects. Mathematics has proved that this is possible. That's the latest state of affairs. If you want to increase the possible number of sides of a regular polygon with n, that's the nature of n, and that is the requirement of your machine. So let us go back to our impossibility discussion. Till now, that part is only left in the whole lecture, that why those particular problems turned out to be impossible. I have discussed only for the pi. Now you know that square root of pi, if pi was constructible, then root of pi was a child's play by the method we have seen. Give me the length which is pi, then I can give you the length root pi. The problem was pi is transcendental, so it's not constructible. Now we come to the other 3 problems. Why they are not constructible? You will see, we will justify mathematically that their constructibility requires the solution of certain equations which are not constructible by ruler and compass. We have to connect these 2 ends only. Only then mathematically it will be justified that those 3 problems cannot be tackled by ruler and compass. So towards that, I've talked about number field already, so I revisit the number field. Now this is a little bit of mathematics, but not very involved one, a very mechanical one. I have tried to bring it down to that level. So what we start is this. We start with a given field f0, maybe the field of rationals. One single segment is chosen as a unit length. And then what do? We do an adjunction of root k0, where k0 is in the initial field, but root k0 is not in that field. Just like you start with a rational field, take the number 2, root 2 is not there, but root 2 is a length that you can construct. So what do we now do? You make new numbers of the form a0 plus b0 root k0, like a plus b root 2. Make all such numbers where a and b are arbitrarily chosen from that field, the field that you already have. Suppose for us, the field of rationals. So I just make x plus y root 2, all such numbers. And it can be shown that this collection again is a number field. And I call it an extension. An extension using that square root of 2, that is not because of 2, because of square root, I call it a quadratic extension. An extension using a 1 square root. And I call it the next field. And it can be shown very easily. It's quite obvious that the previous field is actually sitting inside. The previous field is sitting inside here. all those A0, B0. So this Q is to begin with F0. Then I have a larger one, which is F1. And the members of F1 look like this. Remember, A0 plus B0 into root K0. That's not the end of the row. Now you take some constructible numbers. These are all constructible numbers, no problem with that. A0 plus B0 into root K0. Individually, all of them are constructible. They are product constructible. They are sum constructible. So they are constructible numbers. So take a length of that kind. Now call it K1. Find the root K1. Surely root K1 is not in this field. Root K1 you cannot write in terms of the elements there. It goes beyond just by the previous argument. So what do? So now from this field you choose elements like X and Y and make numbers like X plus Y root K1. All such. Remember, now these X and Y's, they are themselves from F1. So they themselves look like A0 plus B0 root K0. And you are using those as X and Y. So now you see where from this nested root in the expression are coming. They themselves are like this. And then you are having X plus Y root K1. Where K1 is a number in the previous field. That means K1 looks like A0 plus B0 root K0. And you are talking about root K1. So that's how root of root is coming into the picture. But all square roots. Because I know only to calculate square root by my machine. My machine allows to calculate square root, as I have already explained. That remains constructible. And what I am doing is an equivalent algebraic description. And again, that makes a field. And there is no end to this construction. I just keep on doing it. At every stage, I look at a field, number field, choose some element from it, find its square root, it is beyond the field. I make an extension, quadratic extension of that by choosing arbitrary elements from this field and making elements for the new field of this kind, X plus Y root K, where K was a number in the previous field and root K was not there. And XY coming from the previous field, of course. So this actually leads to a kind of tower in the making. Can you see that? See, initially it was because everyone is larger, containing the previous one. There's a kind of tower growing. Right? So repeating this process, we shall reach a field Fn in after n adjunction of square roots. F0, there was no square root, only rational. F1, you took one particular square root, maybe it's root 2. So F1, all the numbers, they have only one square root involved or no root within that. Maximum number of square root involved is 1. Then you took something from it, went beyond this root of root. That means that's what you call F2. So Fn, you have those expressions where n adjunctions of square root is maximum possible there. Clear? This structure is now presented in front of you. F0, F1, F2, on and on and on, Fn, and there is no end to Fn. Fn is not the end point. It just continues. With F0 equal to Q, and this is the formulation of Fi plus 1. Fi plus 1 is Fi Ki plus 1, where this Ki plus 1 is in Fi, but root Ki plus 1 is not in Fi. That's what I have been talking about last 2-3 minutes. These numbers of this form, they are called surds. Surd is just another name of constructible number. Don't confuse with what is usually called surd in class 9-10 books. This is complete nonsense. In mathematics literature, these constructible numbers has another name called surds. So surds are just nested roots. All rational numbers are surds. And then nested roots of that, square roots, as many times as possible. And addition, subtraction, multiplication, division of that. Those filled operations freely with these expressions as far as you can. Whatever you get, take another square root. It opens up a new field. And there you do all possible operations. You get new expressions. Take another square root from any of them. That opens up a further field. And there is no end to this process. It's a kind of tower. So all elements of Fn are surds. And every surd belongs to a surd field of some order. Now there is one important thing to understand. I am not professing that one single Fn is there that contains all the surds. No. See, the field that contains root 2 will not contain root 3. Rationals, you take one particular number root 2, then what kind of numbers you are permitted to make? A plus B root 2. A and B are arbitrary there, but they are rational. So whatever you do with A plus B root 2 type of things, you can never cook up root 3. But then root 3 is another potential candidate for going out of Q. Of course, I can use root 3 instead of root 2 from the beginning, or maybe root 5. So each of them is a different tower. I'm not proposing one single tower containing all of them. No. This is a tower. This is another tower. This is another tower. Infinitely many such towers. Clear? So SARD is the totality of all of them. There's a collection. And these are all constructible numbers. And by its nature, you see, because they are nested roots and nested roots and nested roots, as numbers, they are algebraic in nature. They are algebraic. You can reach them. You can take x equal to such expression and simplify it, just making powers of x to get rid of the square roots in the right hand side. Just like I give you x equal to root 2, as simple as that. You want to make an equation out of it. So of course, one squaring will do. X square equals to 2. Then you get x square minus 2 equal to 0. A polynomial, of which that root 2 is a solution, and hence root 2 is algebraic. That's how, because these are roots of roots of roots of roots, what you ultimately get is x to the power something. That something has to be power of 2, because these are all square roots. There is no question of any other root. There is no question of having cube roots or fifth roots of any other nth root. Only square roots of square roots of square roots, and within them there are expressions. So if such an expression is equal to x, it is not difficult to see that this expression is algebraic. So what I get is that these SARDs are all algebraic numbers. Of course, not the other way around. Cube root of 2 is also algebraic, but that's not a SARD. Cube root of 2, I don't know how to construct. My machine will not allow me to construct cube root. My machine's restriction is square root only. And I am investigating the whole thing with that limitation. Addition, subtraction, multiplication, division, and extraction of square root. Nothing else I need. This is the limitation of my machine, and I'm going to explore that with this limitation, with this geometric limitation, what amount of algebra, what amount of construction, what amount of constructibility I can attain, and whether those 4 problems, classical Greek problems, particularly first 3 of them, whether they fall in the category of this attainability or they remain beyond that. That's what I'm trying to explore right now. Connecting between geometry and algebra. So algebra tells me that this is a construction that I can have here. So root 2 is a sort of order 1. Root 2 plus root 3. That's a sort of order 2. See, that's a number that is neither in the field of this tower of root 2 nor in the tower of root 3. Right? So on and on and on. This kind of towers you think. And with that is a formal definition. X is called a SARD if we can calculate x by a finite number of addition, subtraction, multiplication, division, and extraction of square roots, starting with 1, which is a SARD ex officio. And the constructible numbers, those are also known as SARDs, are those numbers and only those numbers which can be reached by a finite succession of aforesaid type of extension fields. So constructible numbers means those numbers and only those numbers which can be reached by this kind of succession. They are in some of these fields somewhere that can be attained by successive approximation of square roots and beyond, square roots and further number of this kind, a plus b root x, this kind of numbers. The initial field is generated by the single element. I start with that rational, then it can be proved that all constructible numbers will be algebraic. And these SARDs, all SARDs, the collection of all these constructible numbers, they form a Euclidean ordered field. So Euclidean order is something very simple. It is a technical thing. It tells you that every positive number has a positive square root. Assuming that 0 has a square root itself, every positive number has a positive square root. That's called Euclidean order. It's a kind of completion. Like in the ordinary field axiom, you have a LUB axiom for the ordered structure, compatibility. The Euclidean order just claims this much, that every positive number has a positive square root. So in SARD, it happens. Every positive number has a positive square root. So this is a Euclidean ordered field, and I call this field S. Now some imagination is required, visual imagination. So we are really at the crux of the whole story now, mathematically connecting the possibility or impossibility of those constructions in the language of algebra. Where it fails, why does it fail? We will make an equation out of those classical problems, see what the nature of the equation, try to solve it algebraically, and then try to justify that this solution is not attainable in terms of constructible numbers. That will justify, hence, those problems cannot be tackled by constructible numbers, means cannot be tackled by the machines that can only produce constructible numbers, means cannot be tackled by ruler and compass alone. That's the scheme of argument, right? So let me just bridge the gap now. First of all, try to imagine, try to understand, appreciate that all numbers, the numbers you see on the plane, real numbers on the plane, those XY type of things, these X's and Y's, these numbers, not all of them are surds. They are numbers which are non-surds, just like cube root of 2. You can't reach this by this technique that I have told. By taking succession square roots and making number fields out of that, you can never reach cube root of 2. But it is there, it's a real number. So some numbers are certainly not surds, and granted that there is one non-surd, it follows that there are many. Of course, all algebraic numbers are only countable, and this is a subset of that, constructible numbers. So there are uncountably many non-constructible numbers, non-surds. In fact, if X is not a surd and P by Q is a rational, then the product of P by Q and X is not a surd as well. A non-surd multiplied with a rational, which is the surd of order 0, the most elementary, easiest. So if you just multiply a rational with a non-surd, the outcome again will be a non-surd, of course. Negative, otherwise you argue that if it turns out to be surd, then you take that P by Q to the other side. Y is a surd and Q by P is a surd. So their product should be a surd, constructible numbers. So that makes a field. So X becomes surd. That's not the case. Started with the fact that X is not a surd. So that justifies that if X is not a surd, you multiply it by a rational, the outcome is still not a surd. Fine. Now think of these particular definitions. This is the approach of Edwin Moyes, right? Elementary geometry from advanced standpoint. One of the fantastic, most fantastic book I have ever read in my life. Fantastic presentation of all these aspects. And starting with absolutely elementary thing, the book has gone till construction of non-Archimedean ordered field. It even talks about hyperbolic geometry, beginning with the idea of, most elementary concepts of geometry. Anyway, if possible, sometime you consult the book. It's fantastic, really. Okay, so from that book, this particular discussion I'm trying to present to you. So these are certain definitions. Now you take S point. So both coordinates of a point lie in S. S, remember, S is the collection of all that surds. All those, that the Euclidean ordered field, the collection of all surds, constructible numbers. So if a point has both its coordinate in S, we call it a S point. Similarly, S line, a line which contains at least two S point. S circle, a circle whose center is a S point and the radius is a constructible number. S equation, a linear or quadratic equation in X and Y with coefficients in S. These are standard items that I'm going to use in the next argument. And it can be easily shown that this S line is the graph of an S equation, and conversely, or S circle is the graph of an S equation, and conversely, these are routine things, it can be shown. Concentrate on the first four definitions, the requirements. And I go to the most important slide now, the next two slides. It can be shown that these steps of geometric construction in general, what they do, these are the kind of constructions. What new items I get out of the construction? Either I get the intersection of two lines, there's a new point I get, the point of intersection that has to be calculated. Geometrically, I get the new point pinned down when the line intersect. Geometrically, when a line intersects a circle or two circles intersect, I get some new points algebraically which I can calculate. And these calculations, if you can understand, is a linear one, two linear equations, or a linear and a quadratic, or two quadratic equations. What you are doing? Actually, you calculate with the coefficients, and these coefficients are all in S. I'm dealing with those things. right? So drawing a line through 2 points, drawing a circle to center and radius, marking the intersection of 2 lines, 2 circles, or a line and circle. But this will produce new quantities that lies in the field already known to consist of constructible number, or may open up by square root of some constructible number in new field, new extension field. It's very easy to understand that when you have 2 linear equations, you solve them. What are you doing? Working with the coefficients. The coefficients here are all constructible numbers, and solution process in algebra means what? Addition, subtraction, multiplication, division. And if one is quadratic, the other is linear, or both is quadratic, then the solution process may further involve extraction of square root, nothing more. But all these are admissible, and all these will lead to anything that is definitely within the third field, right? With that understanding, as I pointed out already, if P is a intersection of 2 circles, 2 S lines, 1 S circle and S line, then P is a S point. This new P that I get definitely is a S point, in the sense both of its coordinates are constructible. Because when we solve these equations, we actually work with their coefficients and apply the rational operations or extract square roots thereof. Fine. Now I define something amazing. I call it a third plane. So usual plane is E, the Euclidean coordinate plane, the R2, the usual plane. Along with that, I define something called E bar, the third plane. This is the set of all third points in that coordinate plane. Third points, the points both of whose coordinates are thirds, constructible. That's E bar. And then I define third line, which is a usual S line having at least 2 third point, and I take the intersection of that S line with E bar. Set theoretic intersection. That is what I call L bar, the third line. Similarly, I define third circle. I had a S circle. S circle means center is a third point, radius is a constructible length, and I have a circle. That's a S circle. But now I define third circle. What is that? Intersection of this E bar with that third circle. Now try to visualize, my friend. This is the most important thing. Try to visualize how this E bar looks like. How this E bar looks like. Try to appreciate that if you have a non-third, like say this plane, the ordinary plane, on which you have one single non-third plotted, then x equal to that, you take an equation. X equal to a non-third, and take that line. Then on that whole line, not a single S point will be there, because S point require both the coordinates must be constructible. I have taken x equal to 1 non-third, x equal to some alpha, where alpha is a non-third. Then x equal to alpha, the line, the whole line, there is no third point. Like, you can cut the whole plane along this line, a 1 point fine cut through this line. Imagine that I give you some kind of spectacles which will allow you to see only the points of E bar on the plane. Then what do you see? Imagine, just like, you might have been in 3D animation films. They give you a spectacle. Once you put it, you see the 3-dimensional pictures. You take it off, then things are blurred. You see the 2-dimensional imagery, and then you put it again. You see the exact 3-dimensional picture. Try to imagine it here, just like the specs I have given you. Imagine it here. That will allow you to see on the plane. Think in front of you, there is a plane, the R2, and these specs allow you to see the points of E bar only. So the set of all third points, the points of which both coordinates are constructible. Of course, there are many, many such points on the plane which is not obeying this norm. In fact, E bar is full of holes. It does not contain all of any line or any circle. You cannot expect a line, full line, to be made of, in that sense, in the way of speaking, of all points which are always S points. All the points on the line. That is never possible. So once you see the ordinary plane and you draw a line on it, you see it properly. And then you take off your specs Rather, ordinary eye, you see the thing properly, and then you wear your specs, the specs that will filter and allow you to look at the S points only. You don't see the line anymore. You see the S points that were possibly on the line, because it was a S line, there was at least 2 S points. Then only those 2 will see. If it is not a S line, then you don't see it at all. Try to imagine this picture. Miserable picture. The whole plane, as we geometrically accept it and see it, is a kind of connected and continuous everywhere. If not in mathematical sense, talk in terms of English. There's no gap anywhere. There's a whole thing, continuity everywhere. And now I propose to have on it superimposed the idea of E bar, the set of all third points. And if you look at it with some filter that will allow you to see the third points only, you see some discrete points, not a complete line, not a complete circle. You draw the whole circle on the ordinary plane, and then where the specs, you don't see the whole circle anymore. Some third points that are there on the circle, only those are visible. It's a peculiar situation. Everywhere there are holes. But now comes the most important realization. If you investigate this third plane with ruler and compass, if you try to construct things on this third plane, the plane that is full of holes, only the S points are visible. You do your construction on that. You put your spike of a compass on such a point and try to do constructions. With ruler and compass, if you do construction on third plane, you can never tell that any point is missing. That means, although the third lines and third circles, they're full of holes, they never pass through each other where the holes are. Because where they pass through each other, these are constructible numbers that I have already pointed out at the beginning, at the top of this slide. The intersection of 2 S circles, 2 S lines, 1 S circle and S line, these are always S points. Because what I do, I just take the coefficients and work on that with rational operations and extraction of roots. So they must be constructible. So look at this situation. What fantastic situation you have. You don't have the whole of plane. Apparently, it was very clumsy. Only certain discrete points. Those are S points. But this machine, the compass and the ruler, the unmarked ruler, if you do geometry on this third plane, you can do it. There is no geometry on this you cannot do. With this understanding, we propose this theorem. Every ruler and compass construction which is possible in the plane is also possible in the third plane. Ruler and compass construction, because after all, when you put your compass, you put it on a S point, and then whatever you do, these are constructible things, and all these constructible points are there. They are supplied to you, and actually when you use these 2 machines, you deal with constructible points only, S points only. So it can be done. Maybe when you are doing, some points go missing. It's passing through some vacuum, but it will never meet each other. It will never propose to get a new point which fall in this gap, which fall in the vacuum. That will never happen. These new points that these 2 machines can give you as an intersection of lines, intersection of line and a circle, intersection of circle, they will be there on that third plane. So every construction, ruler and compass construction, which is possible in the plane, is also possible in the third plane. If you appreciate that, then take the logical equivalent from the other side. So if something is not possible in third plane, then that is not possible in ordinary plane as well. By ruler and compass, if I can justify that the angle trisection is not possible in the third plane by ruler and compass, then I have proved automatically that it is not possible in the ordinary plane as well. You see the argument? Logical equivalence. Ruler and compass construction, if it is possible in the plane, it is possible in the third plane. So if it is not possible in the third plane, it is not possible in the ordinary plane. So that's what I am proposing to do now in the coming few slides. The question is, in the third plane, does every angle has a trisector? Is cube root of 2 a constructible number, a third? For that, impossibility, I need one simple theorem of higher secondary standard. See, if you take this cubic equation, just a generalization of what you did in higher secondary, for quadratic equation. Connection between roots and coefficients. It's generalized to general n degree, but here I am just stating it for a cubic equation. So z cube plus az square plus bz plus c equal to 0. These are x1, x2, x3 are 3 roots. Then the sum of the roots is minus a. That is known. So I am having this theorem that will use this definition. Sum of the roots is minus a here. Remember, absolutely one-step generalization of what you did in case of higher secondary quadratic equations. Now this result tells if a cubic equation with rational coefficient has no rational root, then none of its roots is constructible, starting from the rational field. So cubic equation with rational coefficient, if it has no rational root, then its roots are not constructible. So before giving the proof, as you can see, 3-4 lines, simple. But before giving the proof, try to appreciate the essence of this statement. A cubic equation with rational coefficient, if it does not admit rational root, then its roots are not constructible. So somehow I have to connect the problems of Greek geometry 1, 2, 3 with a cubic equation with rational coefficient that has no rational root, and hence those are not constructible. That's the scheme now. I have to connect those problem of trisection, problem of duplication of cube, problem of drawing heptagon. Somehow or other, they are all related to a cubic equation with rational coefficient that admits no rational root. That I will establish now. And then this theorem will tell me, therefore, the roots are surely there, but the roots are not constructible. That's why the ruler and compass method every time failed, and it will fail forever. It cannot reach there. It's beyond that. Because its algebraic equivalent is a cubic equation with rational coefficient that has no rational root. What's the proof of this? Proof is very simple. I think just 2-3 lines, you see. So suppose x is a constructible root of that cubic equation given above. It's a constructible root. Then x would lie, constructible means third. Every third lies in that tower, in some of the tower. So there is some tower fk in a chain of f0, f1, f2, f3, fk. In some fk, this x lies. And if it lies in fk, then it lies in all the further. So I take this k to be the smallest one where it lies for the first time. So if it lies in f2, then automatically it lies in f3, f4, f5, but I consider f2 where it lies for the first time. So k is the smallest integer such that this root lies in fk. So it is not below that. It's not in fk minus 1 or further below. First time it appears in fk. Some fk will be there always because it is constructible. Okay, so if it is in fk, then how does it look like? It looks like this x looks like p plus q root w. That's a construction of these fields, p plus q root w, where p and q and w are in the immediately field before, that is in fk minus 1. But the square root of w was not there. That's how I got to the next one, which is fk. So root w is not in fk minus 1, but p, q, w, they are in fk minus 1, and that's how this x look like. Now it is easily proved that if p plus q root w is one solution, one root of an equation, then p minus q root w, that's again higher secondary knowledge, p minus q root w is another root. So the two roots you get, then you get the third root by that result that I've given you. The sum of the 3 roots is minus a. Sum of the 3 roots is minus a. So the third root that you get here is minus a, minus x, minus y. And when you simplify, you see x plus y is equal to 2p. So the third root is minus a minus 2p. The root is minus a minus 2p, but this is independent of root w, and it gets into fk minus 1. It gets into fk minus 1 further down, and that's a contradiction. Because you have taken that it first appears in the roots, they appear in fk. So I think that is quite simple. So forget if you don't understand the proof. Get the result here. A cubic equation with rational coefficient that has no rational root, then these are not constructible. Given that, that's the final part of the lecture. That's the final part of the lecture. So construction by straight and compass alone is impossible if the algebraic equivalent to the problem is this: cubic equation with rational coefficient that does not admit rational root. Now to check that, this is another theorem that will help us. If fx is a polynomial of this kind, nth degree polynomial where a0, a1, they are integers, p by q be a rational root of this equation, then it can be proved, this p and q being prime to each other, if you just reduce it to that level, then p is a divisor of the constant term and q is a divisor of the quotient of the highest power. It can be proved. We'll take the help of this result. Now, immediately we are in a position to justify the impossibility of duplication of cube. So duplication of cube requires the solution of the problem x cube minus 2 equal to 0. We have already seen that starting with a unit cube, volume is 2. So I need a x for which x cube equal to 2. So that leads to the equation x cube minus 2 equal to 0. Look here, cubic equation with rational coefficient. Does it admit rational root? Apply the above theorem. Suppose p by q is the root here. Then according to that theorem, this p has to be a divisor of the constant. Here it is minus 2. And q has to be a divisor of the coefficient of x to the power 3 here. That's 1. So the possible roots here are plus minus 1 or plus minus 2 according to that theorem. But see, none of these 4 values satisfy the equation. So it does not admit rational root. So this is a problem. Cubic equation with rational coefficients that does not admit rational root. And hence, its roots are not constructible by ruler and compass. Settled. Duplication of cube is beyond ruler and compass construction. Come to angle trisection. Impossibility of angle trisection. See, I start with a specific angle 60 degree. Why? Because in third plane, 60 degree angle is there. Equilateral triangle. Equilateral triangle can be constructed in a third plane. Any origin you take, declare it as 0, 0. You take another constructible length, declare it as your x-axis A0. Length is A, then the third vertex, 0, 0 and A0. The third vertex you surely know it is A by 2 and root 3A by 2. Both are constructible because A is constructible. So third plane contains equilateral angle, so it contains 60 degree. So we'll try to justify that the 60 degree angle has no trisector in third plane. I've already proved if something is impossible in third plane, then it is not possible in ordinary plane as well. So I prove it that it is impossible in third plane. And how do I give this proof? Okay, look at the figure. Suppose this red line, if possible, this red line is a trisector. You can see here. Suppose this angle, this CAB, that's 60 degree, and I profess, if possible, suppose this AD is a trisector. Then this has to be a S line. A, the origin, fine. So at least one more S point must be there on the red line. Suppose that point is D. Suppose that point is D. I may not look at the whole red line on the third plane. I can't look at that. But theoretically, at the back of that third plane, on the ordinary plane, this line could have been drawn if it is possible. But third plane, what is my argument? Because it has to be a possible construction, it is a S line, and then there is at least one more point, because at least 2 S point must be there on a S line. So at least one more point, and I call it D. Then I drop a perpendicular from D to F. This F being the foot of the perpendicular of that S point, this F itself is a S point on this so-called x-axis. Already one length is there. This is one. If it is on x-axis, one coordinate is 0. The other coordinate is provided. One coordinate is some length, and the other coordinate is coming from D, the foot of the perpendicular. Both the coordinates of D are surds. So F is a surd. S point. Coordinates of F is surd. If that is so, then AF, both A and F being S point, their length, you can calculate root over this square minus this square. See, once again, root and squared and simplification. So that length is a constructible length, surd. So AF is constructible. Similarly, AD is constructible. If AF and AD is constructible, their ratio, that is cos 20, must be constructible. The ratio is cos 20 because I have taken this to be, to start with, I have taken this red line to be trisector of angle 60. So the angle there is 20. And now I see this AF by AD must be cos 20 because AF is constructible, AD is constructible. So AF divided by AD constructible. So cos 20 is constructible. So what's wrong in that? See, if cos 20 is constructible in this picture, there's a standard theorem, standard result for cos 3 theta is cos 4 cos cube theta minus 3 cos theta. I put theta equal to 20 in this equation. Then I get this equation 8 cos cube 20 minus 6 cos 20 minus 1 equal to 0. And cos 20 is the root of this equation. Clear enough? 8y cube minus 6y minus 1. I want to make it a bit simple. Make another transformation of variable. Put 2y equal to x in that equation, 8y cube minus 6y minus 1, I just use 2y equal to x. So I get this equation, x cube minus 3x minus 1, of which half cos 20 must be a root. Simple theory of equation. And there we are. A cubic equation with rational coefficient that does not admit a rational solution. Once again, you can check with that same theorem, that if p by q is a rational solution to this, then p must be a factor of this minus 1, q must be a factor of 1. So only possible values are 1 and minus 1, and none satisfy this equation. So this is impossible. That means construction of angle trisector in third plane is impossible in general. So construction of angle trisector in ordinary plane is impossible in general. Finally, regular heptagon, a very similar argument. Construction of regular heptagon by ruler and compass. So heptagon, you know, x to the power z to the power 7 minus 1 on the plane. The roots of that on the unit circle, that would give this. So suppose these are the roots I'm trying to find and trying to justify whether they are constructible or not. Then one root is 1, clear enough. For the others, I just divide z to the power 7 minus 1 by z minus 1, and I get this polynomial. Simple, z to the power 6 plus z to the power 5, etc. I just club it, make it a little bit simplification, because I have to bring it down to degree 3 polynomial, right? So what I do is just simple, dividing all through by z cube and do some ordinary algebraic manipulation. A cube plus b cube, I just write it as a plus b whole cube minus thrice a plus b, and so on. A square plus b square, I write as a plus b whole square minus this twice a into b, and then simplify this, take this z plus 1 by z as a new variable y, and I end up with a cubic equation with rational coefficient once again, y cube plus y square minus 2y plus 1 equal to 0. That does not admit. Now you see, all these three problems, they are in a typical algebraic category. They are referring to a cubic equation, rational coefficients that does not admit rational solution. That's why none of these roots are constructible. That's why these problems were beyond construction. That's that proof is just the same thing that I have told you. It is done directly here by choosing R by S without using that theorem. That theorem makes things easier. Instead, here I have chosen, if possible, let R by S be a rational solution, and I've shown the contradiction. Very similar. So that, I think, settles all the issue that we started with. But then this is not the end of the story. I'll take 2 more slides to explain you. If you give me 3-4 minutes, can I have 3-4 minutes more?
Yes, sir. Yeah.
Sure. So, the very nature of mathematics is this. That's a great saying by George Bernard Shaw. Who else can say such things? That mathematics is a bad subject. It never solves anything without giving rise to 10 more problems. And as a mathematician, we are really delighted with this character of mathematics. So here comes an epilogue to this entire story that I have been telling you from yesterday. The whole story began with the idea of collapsibility of compass and so many things related with that. Now you know, perhaps, the restriction of collapsibility, their importance, their, the limit of this collapsibility, the transcending the limit. If I use some other machines, then what I can do, all thing has been discussed. But there were certain people in the Middle Age, in 10th century, one Persian mathematician, Abul Wafa, perhaps he was so disturbed with this collapsible compass and its construction, its failure to prove this or that, he just thought the thing some other way around. He started thinking about straight edge and rusty compass construction. So it's just the opposite, a dual of a collapsible compass. Collapsible compass is what you lift and it collapses. The rusty compass, it's theoretically such a design, such an instrument, such a compass that you just cannot change its radius. It's a fixed thing. Rusty, you just cannot move it further. It just gives you one single radius to draw. Of course, with this construction, now he tried to explore the horizon of the possibility of this construction. There is a straight edge and a rusty compass, what construction you can do. So these are now things which are part of what is known as recreational mathematics. There's a fantastic book by Martin Gardner, Mathematical Circus. I refer you to that book for these kind of things, further discussions. I'll just show you one interesting discussion, one interesting construction only, elementary but fantastic, by rusty compass. Of course, one assumption you have to make. See what construction is being professed here. A line is given and a point outside a line is given. You have to construct a line parallel to the given line through the given point. That's a dotted line that is to be constructed. Given the line on below, and there's a point P given outside it. And you have to do it by rusty compass. Of course, one assumption is there that this gentleman might have many different rusty compasses with many different specific opening, because if this point P is far away from this line AB, then one particular rusty compass with one particular opening will not do. I need a rusty compass. One rusty compass will do, but such a compass I need so that putting the spike on P, and if I draw this circle, as you can see here, the large arc there, then that actually cut the other line. So the opening from P to A, that length I need to have. So assuming that I have such a rusty compass at my disposal, then I can do this construction in a very, very elegant manner with this rusty compass. We just put the spike at P and just use the compass to draw a large arc so that the arc somewhere intersects the given line. Here it is intersecting at A. So the point A is achieved. Then with the point A, now put the same rusty compass, no change in the opening. So I put the spike at A and draw an arc at B. So the length is same, the same radius. Then I put the spike at B and draw that arc that cuts the larger arc at some point C. And then I join just P and C by my straight edge. And that's the line parallel. Because what I have constructed basically is a rhombus, right? All the four sides equal. All the four sides are equal. PA equals to AB equals to BC. So that's the rhombus I have constructed. That's how the other side PC is parallel to AB. So that's a rusty compass construction. Similarly, that's not the end of the story. There's a gentleman, Mascheroni, who, there's another gentleman much before him, Mohr. Nowadays, these are called Mohr-Mascheroni construction. He's a gentleman from Italy who proved that all geometrical construction possible by straight edge and compass can be made by compass alone. You don't need straight edge, of course. Straight edge allows you to draw the line. Compass will not allow you to draw the line. In that case, you have to make this understanding. You have to accept this, that if I get 2 points on a line segment, then I must consider the line segment has been achieved. Compass will not actually allow me to draw that, but mathematically, achieving a line segment is equivalent to achieving 2 particular points on it. Once I get 2 points on it by compass, I assume that the line segment is there. If you accept that, then any construction possible by straight edge and compass can be done by compass alone. This is called Mascheroni construction. So I show you 2 simple Mascheroni construction, and again refer you to that fantastic book of Martin Gardner. So this is a Mascheroni construction of doubling the length of a segment. You are given the segment AO. As you can see, it's not drawn. A and O are 2 arbitrary points. The segment AO is there. You want a third point C such that AC is twice in length of AO, and it can be done by this. And mind you, this is ordinary compass, no more rusty. Rusty business was done by Abu Luefa. This is just ordinary compass. And by that, you are trying to do this construction. This is very simple. With O as center, OA as radius, you draw a large arc of the circle or the complete circle if you want. And then you just put the compass with the same radius with A, P, and then P, Q, and QC. All you are doing is drawing 180 degree, 60, 60, 60. So of course, the point C will be exactly in the other side of O than A, and the distance will be twice because this is the diameter of the circle. So elegant. A little bit more complicated, but equally elegant is the construction of halving the length. It was duplicating the previous one, doubling the length. This is halving of it. So AO is given. You want to find a point. This construction that I have tried here is not very accurate. Actually, my controlling of drawing was not perfect. As you can see, this point R supposed to be the midpoint of O if you do the construction in a correct manner. The method is correct. There is nothing wrong in it. But the actual drawing that I tried with my bare hand is not that accurate. So R is not exactly the midpoint, but the construction method is okay. That will give you the midpoint. The method you can see is very simple. With A and O given, you first do the construction of the previous one. You just go to the point C in exactly the same construction as you've done right now in the left-hand side. So you get the point C, but now with point C as a center and CA as radius, you draw this large arc that cuts the initial left-hand side circle at the point P and Q. Then with P as a center and PA as a radius, you draw the arc in the middle, as you can see. And with Q as a center and QA as a radius, you draw another arc. They will meet at the point R, and it's a routine geometry. Maybe you can try it later to prove that this construction leads to this fact that the point R found this way is the midpoint of AO. And finally, Jacob Steiner. what he told is more amazing. All construction in the plane which are possible with a straight edge and compass are possible with straight edge alone. That was compass alone, right? More machinery construction. Now here is a gentleman who says everything can be done by straight edge alone, provided one fixed circle and its center is given. So one particular circle means that is the purpose of using your compass. It's a complicated theorem, not getting into that in details. Those who are interested can check Jacob Steiner. You write Jacob Steiner and this construction process, you will find many, many things in internet. So that's how these are now the frontiers of the problem. And there I end. Thank you very much. These are the references that I told you.
Yeah. Thank you so much, sir. And
Alapon, can you keep a little bit more the reference page? It has vanished from my screen. I don't know why.
yeah, it has vanished
Okay.
from.
Okay,
Yeah, now it's.
I just bring it back because people may be interested to know about these references, the books. Yeah. There is it. So that's the book. Courant, Robinson, Stewart, What is Mathematics? Joseph Gallian, Contemporary Abstract Algebra, our team. These are very good algebra books. But there are little reference of these impossibility constructions in the light of algebra. What we have done, basically, it is done in the postgraduate abstract algebra class in field extension, done in a nutshell manner with only that theorem of quadratic extension. In field theory, what I tried is to bring it down and, punch the whole story of it, the very evolution, the very genesis of the problem and the present state of affairs. And that's the book I have referred to, Elementary Geometry from an Advanced Standpoint by Edwin Moyes. That's the book of Martin Gardner. There is another fantastic book, 100 Great Problems of Elementary Mathematics, their solution and their history and solution, Henrik Dory. And these are some internet elements that you can find. Constructibility of Regular Polygons by this gentleman, Eckhoff. This is the book Hartson, Robin Hartson. That's a 2000 book. Euclid, Geometry, Euclid and Beyond, Springer book. It's a book by Ian Stewart, Galois theory, from where I got that reference to Ramanujan, and then I consulted the Ramanujan diary myself and found those things. So these are the complete list of reference. You can take a picture if you want to and refer to these things later on. Thank you very much.
Yeah, sir, let it be shared like that for some moment. They may take notes or they may screenshot that. Yeah, I myself was going to ask that. Yeah. So now I call Dr. Somode, postdoc fellow at IMSC Chennai, to make a sum of what we have learned in 2 days. Yeah. It's up to you.
Hi. Hello, sir. Thanks a lot
was
for.
Was it comprehensible? Could you follow what I tried to make you understand?
Yeah.
Oh, that's good.
Yeah.
From my end, I can't see any face. I can't, once we teachers see the face of the students in front of us, we can read whether they are being able to follow or not. In this confounded system, that is completely missing. So it's a very peculiar situation for us. We can never actually gaze that whether the thing is being understood or not. That's why I'm asking you. Okay. Go ahead, please.
Somoda, your video is inverted. Can you?
No, I see him, right?
Oh, I don't know.
Yes, I also see him, right?
Okay. Then that might be.
Maybe Alapon, you can put your screen somehow. Okay.
Yeah.
So I think what Professor Mukhopadhyay has said in his 4 talks is very much clear to most of the students. But still, as per the format of the program, I would go over briefly some points which I think are somewhat important. So, so the speaker starts with the motivation, how he started thinking about all this. So it was by a question by his daughter, and she asked about the importance of a divider. Okay, so why a divider is needed. And so from there, he starts to think that what is the difference between a divider? What kind of constructions can be done differently with a divider and a compass and a straight edge, these things. So, so one point which is very much stressed in the whole of these lectures is formulating a problem correctly is very important. When we say something mathematically, it should be mathematically correct problem. Okay. So a problem can be classified into 3 types. Okay. The first type would be a problem which is already solved. Then the second type would be it's still unsolved. And then among the unsolved problems, you can have 2 types. One is solvable and the other one is unsolvable. So this is very tricky. I mean, when you don't know a solution of a problem, how to determine that problem is at all solvable? Okay, it is different. Till now nobody has tried or nobody has achieved a solution. This is different from the fact that it cannot be solved. So here we'll see. I mean, we have seen a few problems which are unsolvable. Okay, let me go over these. So the first thing which was discussed is like the difference between the approach towards geometry. So in the time of Greeks, what they were doing were these are said to be elements from synthetic geometry. So they did not think about, or maybe it was not required at that point of time, that you know a length. Given a segment, there is no requirement to know the length of that segment. So, but now we are not distinguishing between a segment and the length of the segment, and this kind of approach is called metric geometry, which is more modern. So at that point of time, there were no notion of length, so they use this ruler. So by a straight edge or a ruler, we mean it is unmarked. So there was no length. There is no marking on the ruler. Okay, it's just a piece of straight scale, or right. And the second type of instrument that they had is collapsible compass. So it's a compass, but when you lift it from the paper or the ground, it gets collapsed. Okay, so these 2 instruments were used to draw different diagrams. Okay, and it has been shown that almost all possible constructions were made by these 2 simple instruments. Okay, only a few, namely these 4 type of constructions which were not solved at that point of time. Okay, let me say which are these. So the first problem was, given any angle, how to trisect. Okay, so given an angle theta, how to draw an angle which is theta by 3. Okay, it looks to be a very simple problem, elementary problem, but it is a very tough problem, it seems. The second problem was duplicating a given cube. Suppose you were given a cube, you want to make a cube which is exactly same. So when you take these 2 these 2 same cubes, you have a bigger cube of volume 2a cube. Okay, so you have first a cube which is the volume is a cube. You want to create a cube which is you duplicate the given cube. Okay, so the total volume would be 2 times a cube. Okay, the third problem is constructing a regular heptagon. Heptagon means a 7-sided regular polygon. And the third problem was constructing a square. So given a circle of some area, you want to construct a square with that given area. Okay, So this is the four. These are the four type of problems that were not solved by the Greeks. But then, if they had, I mean, not just using these straight edge and compass, they have tried other type of instruments like nooses and tomahawk, and then right angle frame with a cross and a slider. So using more instruments, they were able to trisect the angle and duplicate a cube, and also construction of cube root using a marked ruler. Okay, and he has talked about Menelau's theorem while this construction of cube root thing. Also, he talked about the work of Euclid, and how he constructed regular pentagon and then regular 15-gon and these things. Okay, so this was the content of his first and second talk. Now, starting from today, we have seen Ramanujan's. So Ramanujan's approximation to root pi was last time, yesterday, and so today, what he has talked about is unsolvability of a problem. So basically, he started with a theorem of Gauss in 1796. Okay, so what is the statement of the theorem? It says that for odd prime p, the regular p-gon is constructible if and only if p is a prime Fermat number. And what is a Fermat number? So p would be of the form 2 to the n plus 1. For example, the first few Fermat primes are of this form, are these. So 3, 5, 17, 257, and 65,537, and so on. Okay, so initially it was believed that any such Fermat number are going to have, going to give us primes. But then it was shown that the next prime, in fact, the P5 was not a prime. Okay, so and he also showed us many other Fermat numbers, and we have seen that these are quite large. I mean, factorizing these large numbers is a very big problem even today. Okay, and right, so Gauss has proved in 1801 that a regular polygon of n sides is constructible if and only if n has the form 2 to the k, or 2 to the k times p1, p2, pi, where pi's are distinct Fermat primes. Okay, so this is a more general theorem than the previous one. And then Wanzel in 1837 proved that it is not possible to double the cube using the ruler and compass. And then Lindemann in 1882 proved that pi is transcendental. So these are some results that he has quoted. Now let's come to what is how do you define a constructible number? Okay, so a real number alpha is called constructible if by means of a straight edge, a compass, and a line segment of a unit length, given length, we can construct a line segment of length mod alpha in a finite number of steps. Okay, this is the definition of a constructible number. Now, let me go over another definition of a constructible number, which is basically SARD. So, yeah. So let me formally define what is a SARD. So we start with the number field F0, which is the rationals, and then suppose a unit segment is also given. Now you choose some K0 from your field F0, which is you can take it to be Q, rational numbers, such that root of K0 doesn't belong to F0. Okay, so now you for example, you can take K0 to be 2, so root 2 doesn't belong to Q, and you consider these numbers of the form A plus B root 2, where A or B are rationals. So you get a field which is not exactly Q, but an extension of Q. Okay, so in this way, for other numbers, say P naught, you can construct root of P naught, and so that root of P naught is not in the in the previous field, and you input again get a extension of the field. So in such a way, in finite steps, whatever you get, so you have a tower of extension of fields. Okay, so starting with Q, you can have, so suppose Q is F naught, then you can have F1, F2, Fn, like that. And any such Fi is called a surd or a surd field. And the elements of these Fis are called surds. For example, root 2 or root 2 plus root 3, these are our examples of surds. Now, how do you say that? I mean, so suppose given such a tower of extensions, you take, suppose, some surd from one of the Fis, there is a notion which is the order of that surd. Okay, so for example, in root 2, suppose you take root 2, you can see there is a minimal tower, say Q, contained in Q root 2. Okay, so you can reach root 2 by a tower of length 2 minimally. So the order of this surd root 2 is 2. And another example would be root 2 plus root 3. Okay, to achieve root 2 plus root 3, you have to have at least a tower of length 3. So the tower would be Q, and then Q included with root 2, and then Q with root 2 comma root 3. Okay, so you have a tower of root length 3. So root 2 plus root 3 would be a surd of order 3, like that. And so our definition for a constructible number would be surd. So the surd and a constructible number will be equivalent. Okay. Now it was there were many definitions actually. So now it is clear that not every number is.
Shomo, if I may interject,
yeah.
I think root 2 plus root 3, I think it should be a tower of degree 2. So you have a Q, you take 2 from that and make root 2 extension by root 2, and in that field Q is still there. So you make a root 3 there, and in the next, when you are extending that Q root 2 by root 3, in that tower itself you will get both root 2 and root 3. So the sum of root 2 plus root 3 is available there. In F2, start F0. I don't know if you
okay, so
the first one has 1, then it is 3. I think you are telling that, right?
Okay,
because I told the first one rationals as yeah, that's what I wanted to point out. So the people should not be confused. Mathematically, okay, but the first one I called 0. F0 in the sense that they are surds of order 0, and then it is 1, and then it is 2 in that sense. So that Fn is of order n. That's it. Okay, go ahead. It's fine. You are doing a nice job.
So according to you, root 2 should be of order 1.
Yeah.
And root 2 plus root 3 is order 2.
Just a difference of nomenclature, you know, beginning point. Beginning with 0 or beginning with 1, that's all.
Sure. So yeah, it's true that there exist numbers which are not surd. For example, cube root of 2. Okay. And if you consider the field of all surds, it's true that this set of all surds form a Euclidean ordered field. Okay, and this field S, we denoted by S, this is a proper subset of the set of the field of algebraic numbers, and also this is properly containing the field of rational numbers. Okay, so Q and the algebraic numbers, this is in strictly in between. Okay, so now there are some definitions. The first is, what is an S point? So a point, by a point I mean a point in the plane R2 with both the coordinates in S. Okay, we will call such a point to be an S point. A line which contains at least 2 S points would be called an S line. A circle whose center is a S point and also the radius is also in S is called a S circle. A linear or a quadratic equation in X and Y with coefficients in S is called a S equation. And what is a surd plane? We denote it by E bar. this is the set of all surd points in R2. Okay, so surd point, again, what is a surd point? A point with both the coordinates in S. Okay, so you consider all such points in the plane R2 such that both the coordinates are surd points. Okay, you denote it by E bar. And now what is a surd line and a surd circle? You take a usual line and intersect with this E bar, you get a surd line. And a usual circle intersected with the surd plane E bar is a surd circle. Okay, so right, so and also he has demonstrated that the surd plane E bar has many holes. Okay, for example, he has taken some non-surd point in the x-axis, and he constructed this line which is parallel to the y-axis, and none of the points of this line would be a surd point. So like this, there are many holes in the plane which are not surds. Okay, so basically the surd plane is a very small subset of the usual plane R2. And also he said that every ruler compass construction which is possible in the plane can also be done in the surd plane similarly. Okay, now we have the main, I mean the final theorem of these talks. And so I forgot whose theorem is this. This is by Gauss. Okay, so let me state the theorem. If a cubic equation with rational coefficients has no rational root, then none of its roots is constructible starting from Q. This is by Gauss.
Maybe, I'm not sure. I have to check. This is in standard,
Okay.
standard modern literature.
Okay. Okay. So let me again state this theorem. Suppose you have a cubic equation with rational coefficients, and this equation does not have a rational root. Okay, then none of its roots is constructible. So by using as corollaries of this theorem, we have, I mean, they have proved that the three type of problems that we discussed, we had 4 problems.
I think
and
this
3
theorem
of
is
them
by Wandjel. This theorem is by Pierre Wandjel in his 1837 paper. Yeah.
Okay. So how to show that duplication of cube is impossible? So to solve this problem, we end up at the end to the equation x cube minus 2 equal to 0. And it has shown that none of its roots are rational. Though the coefficients are rational, the roots are not rational, and hence duplication of cube is impossible. For trisection of 60-degree angle, they have arrived at the equation x cube minus 3x minus 1 equal to 0. Okay, and the coefficients are easily seen to be rational, but the roots are not rational, and hence trisection of 60-degree angle is not possible in surd plane, and hence in R2. And for the regular heptagon, construction of regular heptagon, they have arrived at the equation y cube plus y square minus 2y minus 1 equal to 0. Again, the same, the coefficients are rational, but not the roots. And hence these problems are unsolvable. And finally, to end with, he mentioned about some other atoms of constructions, of different constructions. So one of them is using a straight edge and a rusty compass. So what is a rusty compass? The compass is fixed. You cannot move the length. And the second one is only by a compass. And it was shown that any construction which can be done by a straight edge and a compass can can also be done using only just a compass, because the role of a ruler is to draw a line. So given once you have 2 points, even if you don't draw the line between the 2 points, you know that the line exists. So if you remove the ruler, then also the constructions are okay. And the third type of construction is a straight edge with a given circle with a center. Okay, so now these are part of recreational mathematics. and not very, I mean, not very much research is being done, but it's good to read these things. I think that's the overall basics. Okay, thank you.
Yeah, very nice.
Yeah, thank you,
Over to Alok.
Sumodha. Yeah, 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 yeah. Thank you, Sumodha. It was a very nice gist of the lecture. And let us move to the question answer session. Omlan, YouTube channel. The name of the channel is Karilip. We are going to publish this whole lecture in 4 sessions and in some days. And we have already uploaded the previous lecture by Pigeonhole Principle by Satyanarayan Reddy. We have also Facebook page. The name of Facebook page is Kareli Math Club of MTTS Alumni. We are also making a Google group, Kareli Math Club of MTTS Alumni. We are spreading a Google form so that whoever interested, they can fill that and they can join our group. We also have constructed a website, Kareli Math Club of MTTS Alumni. That's link will be shared on Facebook page. So for more updates from for Karelip activities, please share to our YouTube channel, like our Facebook page, and fill the Google form so that you get connected to our Google group. Also, we are going to post a feedback form on Facebook and also on YouTube live chat or YouTube chat, so that the students who have already seen and want to contribute, or in way they can say their views on these lectures, so they appreciate it, or in which way we can develop it more. So please give your valuable suggestions. And yeah, again, now I call Tamognokar to give a vote of thanks. Please be
Yeah,
brief, and we are
Amlan will
running
do
out
that.
of
Yeah.
time. Okay. Yeah, Amlan. Sorry. Yeah, Amlan, please.
Uh, Thank you. So, good afternoon, everyone. I am Amlan, and I am here to present the vote of thanks for the lectures. First of all, I would like to thank our guest speaker, Professor Parthasarathi Mukhopadhyay, for taking out time from his schedule and enlightening us with his knowledge in the domain of this constructibility topic. Thank you so much, sir, for introducing us to the deeper insights of such a topic, from the historical geometrical construction to the justification of algebraization of the geometry. Thank you, sir. I would like to thank Professor A. Jayanthan Reddy and Professor A. Satyanarayan Reddy and Professor A. J. Jayanthan for constantly guiding us as our advisors. Thank you so much, sir. And then I would like to thank Professor Vishnu Namboothiri for technically supporting us in the best possible way. He gave, without which means it was not possible to reach such a wide range of audience, whether in Zoom or in YouTube live chat. Then I would like to thank the person behind inspiring thousands of young minds to not only think, but discuss and appreciate mathematics. Yes, I thank Professor Kumareshan for such a beautiful video message, encouraging all of us again. Thank you, sir. I thank Professor Ajit Kumar, the trustee of the MTTS Trust, for informing us about the MTTS Trust and its activities the previous day. I also thank Professor Bhava Sharma, Professor Sukumar Daniel, Professor Shamik Paul, and all those who were directly or indirectly helping us in the best possible way. I would really like to thank MTTS Trust for supporting our club, for not only conducting this seminar, but also for constantly encouraging us to do activities like this. But most importantly, I would like to thank the listeners, the participants, both in the Zoom meeting and the YouTube live stream. Their participation made this lecture active. Thank you all. I would also like to thank Zoom meeting for giving us such a quite comfortable platform for the conduct of this lecture. Finally, I thank the members of Kareleaf and the organizing committee for the smooth organization of this lecture. Thank you everyone for spending the beginning of this year with us, And I wish you all a very happy and prosperous new year. Thank you.
Okay.
Okay.
So
Yeah.
on behalf of Kalilif, I thank Amlan for doing all this job, sorting out the questions out from YouTube and organizing all those things with proper manner and giving for this vote of thanks to all of them. Okay.
Okay. Sir, see you soon.
You,
Yeah.
ভালো থেকো সবাই। So I leave. I take your leave now.
Yes, sir.
Yes, sir.
Actually,
Yes,
it is very energetic, sir. All the time we are very energetic.
Yeah.
Even last minute, tak. That is wonderful to see.
Thank you. Thank you very much.